Hello, I'm Professor John Kelly, and this is the Weber Auto YouTube channel. Today I'm going to show you an amazing tool that somehow I have never used before, never heard about, and it is the Milli-Ohm meter. Now, I had never heard of a Milli-Ohm meter until a few months ago when I was reading an article in Motor Age magazine. I'm a contributing editor to Motor Age magazine now and again, and there's an article written by another contributing editor, Mr. David Macholtz. I hope I'm pronouncing that correctly. He's a Toyota T10 instructor out of Suffolk County Community College in Selden, New York. And the article is about Mega-Ohm meters and Milli-Ohm meters. Now, if you do any work on hybrid or electric vehicles, you probably have heard of the Mega-Ohm meter or Giga-Ohm meter, the Fluke 1587 meter back here. And I've had one of these since 2007, but I'd never heard of the Milli-Ohm meter. So let's take a look at why this thing is so cool and why you may want one if you do any type of electrical diagnostic work, not just on hybrids, but any type of electrical diagnostic work. I think once you see what this thing does, you may want one. Now, this is a very expensive tool. It's around $1,200 to $1,300 depending on where you buy it. Okay, just some basics about an ohm meter. An ohm meter has really never been a very useful tool in my opinion, because all it would do is show you if a circuit was open or not open. The resistance value that you would measure with an ohm meter could be inaccurate if the power was on, which of course the power in the circuit is always supposed to be off when you use an ohm meter, but I've never really trusted ohm meter readings in all of the time I've been a service technician and a professor. So we will compare just a regular ohm meter reading to the milli-ohm meter in this video. The Mega-Ohm meter, the Fluke 1587 meter, we will come back to in a different video. Okay, if we use just a regular ohm meter, a high quality Fluke 87 Series 5 multimeter, and we rotate the selector dial to the ohms position, we can measure resistance. And I have a piece of wire right here, just a small piece of wire. It's 39.3 inches long, which is 1 meter in length. And we connect some good quality meter leads to the meter. I've got alligator clips on the ends of these meter leads. Whenever you measure low resistance values with any multimeter, you should zero out the meter to compensate for the resistance of the meter leads. So on the Fluke 87 meter, there's a relative button with this little triangle or the delta symbol. We just push that, and now with our meter leads connected together, we are reading 0 ohms. All right, now if I come in with our 1 meter long piece of copper wire, and I connect 1 meter lead right there, and the other one on the opposite end, we are reading 0.1 ohms resistance for this 1 meter length of wire. This wire here that we'll measure next is 1/10 of that, so it's 100 millimeters, and if we measure its resistance, I get the same 0.1 toggling to 0, so almost the exact same reading with the 1/10 of the length. All right, then I have a 10 millimeter long piece of wire right here, and we'll just clip that in here, and I'm reading 0 ohms. Okay, so this meter wasn't designed to read real small resistances. Clear down to 0.1 ohms is its resolution, which for most automotive work is fine. But let's take a look at where measuring smaller resistances than 0.1 ohms would be possibly valuable. Now let's do the same thing, but with the Milli-Ohm meter. Now this Milli-Ohm meter is from a company, a Japanese company, I'm probably pronouncing it wrong, Hioki or Hioki It's model number RM3548, and it's called a resistance meter. And this will measure clear down to 0.1 micro-ohms. So milli-ohms is thousandths of an ohm. Micro-ohm is millionths of an ohm. This will measure 0.1 micro. That's 100 nano-ohms it can measure at its finest resolution. So incredible accuracy. Well, let's prove it. The Milli-Ohm meter uses 2 meter leads with alligator clips, of course. But these meter leads, if you look at them, have 2 wires per meter lead. So when you plug in the meter leads to the meter, there's 2 wires per lead. Okay, so let's measure this 1 meter length of wire. We will turn on the Milli-Ohm meter. There's an optional temperature sensor here for the meter, and I would highly recommend that you purchase that. Otherwise, you have to do a calculation to compensate for whatever the temperature of the conductor is that you're measuring. The meter will assume that it's at a certain temperature, and then if that temperature is wrong, then you have to do a compensation calculation to determine the correct resistance. With the temperature sensor, as long as the meter, the sensor, and the conductor and the leads have all been in the same area for around 6 hours is what they recommend, to let everything stabilize to the same temperature, then the meter will measure the resistance of the air in the room. That will be the same temperature as the part that you're measuring, and then the resistance value that it comes up with will be accurate, because resistance is affected by the material it's made of, the temperature of the material itself, the length of the material, and the cross-sectional area of the material. So let's measure this 1 meter long piece of copper wire. The instructions that come with the meter tell us that when you take a measurement that you should wait about 10 seconds to let the meter stabilize and come up with an accurate reading. So this Milli-Ohm meter is showing us that this 1 meter long piece of wire has a resistance of 53.06 milli-ohms. Now that's 0.5306 ohms. Now our other meter, our Fluke 87 meter, that wasn't designed for this type of low resistance readings, was measuring 0.1 ohms, not 0.053 ohms. And the rule, of course, is to round up. So in roundup, mathematically, 0.1 was correct, but this is 0.05302 ohms, 53 milliohms, 53 thousandths of 1 ohm. All right, now, if 1 meter is 53 ohms, then 1/10 of the length of that wire, so 100 millimeters, should be 5 milliohms. So let's try this. Let's take the 1 meter length out. Let's put in the 100 millimeter, or 1/10 of a meter, and look at that. We get 5 milliohms. How cool is that? So 1/10 of the resistance, which of course it should be. If 1 meter is 50 milliohms, then a 1/10 of that should be 5. And a 1/10 of that, this little 10 millimeter long piece of conductor I have right here, copper wire, should be 0.5 milliohms. So let's measure it next. 0.59. It's a little longer than 10 millimeters. 0.5 milliohms. That's incredible accuracy. Now you might be wondering, well, how is that useful for on-car diagnostics? Well, in a hybrid vehicle, which is why Toyota is recommending this tool, you have a stator winding for MG1 and MG2, and for any vehicle with stator windings. So any hybrid or electric vehicle is going to have stator windings of some sort. It could be this individual wire wound stator, like this older design stator right here. And we can come in, there's actual Toyota specifications to come in with this milli-ohm meter and measure the resistance of these windings. So let's do that next. All right, so I'm going to take this meter and go from the U phase connection to the V phase connection. And we are reading 104.3. Let it stabilize for 10 seconds. And notice that this is at room temperature here in the shop, which is pretty hot, 28.3 degrees Celsius. So the U to V resistance of the stator windings is 104.4 milli-ohms. Now that is a 12 strand connection. So there's 12 wire strands there. Now let's go from U to W. Remember, we were at 104.4. Now we're reading 104.2. And the Toyota specification is there should be no more difference than 2 milliohms difference between each measurement. We were 0.2 milliohms different between those two. Now let's go from V to W, 103.9. That's still a 0.5 milliohm difference between the highest reading and the lowest reading, which means this stator is not shorted. It does not have wires that have shorted out, overheated, lost their insulation, and shorted out and are touching each other. But that is something that can happen on cars. And I have a 2002 Prius right over here that we will go measure. This vehicle has a problem with its transmission. There's something wrong that caused the vehicle to lose power, and now when you try to drive it, it's really jerky. It goes as you try to move it. And I believe that it has a shorted stator. And so we will use this tool to measure that. But before we do that, let's look at a different style of stator. A newer design stator is called a hairpin style stator, and it doesn't use the small little wires like we saw in that earlier Toyota stator. This is out of a second generation Chevrolet Volt, the 5ET50 transaxle. But the latest transaxle from Toyota also uses this hairpin technology. What we mean by hairpin technology is each one of these big heavy pieces of flat wire are actually shaped like a hairpin. It's a U-shaped piece that has been bent, laid in place, and then welded together on the back here with another hairpin stator element. And now we have all of these individual welds that can have potential poor connections. And so we can also use this same milli-ohm meter to measure the resistance of this style of stator. So let's do that. Let's take a measurement from U to V. Notice now we get 34.8 milli-ohm, much lower resistance than we had before on the wire wound stator. Okay, now let's go from U to W, 34.68 milli-ohms. And then W to V, 34.82. So all of these are easily within the 2 milli-ohm spec that Toyota gives us. I don't know what GM would give us for a specification because I have not seen this tool used or called for in any GM Diagnostics yet, but I'm sure they will. So this is a GM stator, the other one was a Toyota, but both of them have used both the wire wound and the hairpin style welded stators here. What we're looking for is consistency. We want each measurement across each phase to be very close to equal. A tiny bit of difference is okay, but not not a lot. Now, before we go over to the car and take some measurements of the stator windings in the vehicle, I want to show you a few more things that are amazing about this milli-ohm meter. So I was wondering, how accurate can this thing be? And so I got just one of my alligator clip style jumper wires here, and I stripped off the insulation for about 50 millimeters of the length of this jumper wire. Now I counted, there are 24 strands of very fine wire in this flexible jumper wire. So let's measure the resistance from one end of this jumper wire to the other with all 24 strands intact, and then let's start cutting one strand at a time and seeing what happens. All right, for the entire length of this jumper wire here with all 24 strands, we have 36.44 milli-ohms of resistance. Now, if I just come in and pick out one wire strand, I'm going to come in and cut that wire strand, and let's watch what happens to the resistance reading here. So we're at 36.42. We cut the wire strand, and we go up to 36.54. Now, the reason we went up is because these wires are in parallel with each other. So every time you put wires in parallel with each other, the total circuit resistance goes down. So now the circuit resistance has gone up. So now we're at 36.50. Let me pick out one more wire strand. 36.49 right now. And we cut it. And now we're at 36.65. So we went from 36.49 to 36.65, roughly 0.15 or 0.16 milli-ohm per strand. So I've cut two strands. So now I can predict what will happen when I cut the next one. If we go up by 0.16 milli-ohms per strand, when I cut the next wire, we should go up to 36.81, somewhere right around there. So I'm going to come in, cut the wire. Here it comes. It's cut. There we go. 36.81. Exactly predictable. Is that incredible or what? So we can get right down to determining wire strand resistances and how many wire strands are broken in a length of wire. So another incredible thing here. This meter can tell you how long the wire is. So there's a length button right down here. If I go in and push that button, turn it on, we punch in the resistance per meter. Now we measured roughly 50 milli-ohms of resistance per meter in this copper wire earlier. So now, if I hit enter, the word length shows up on the screen, and I can come in and connect our meter leads to this 1 meter length wire, and now it tells us that it is 1.0662 meters in length. So based on the resistance of the wire, it can tell you how long the wire is. That's really cool. So now let's go to this 100 millimeter length wire. 100.1 millimeters. It's now showing us. And now let's go down to this 10 millimeter length wire. There. 11.06 millimeters. Now I still need to think about it. I'm still wrapping my head around how cool this meter is. There's got to be some really cool diagnostics things that we can do with this besides just check for shorted stators on a hybrid or electric vehicle. All right. One of my coworkers, Will Spiegel, was here in the shop yesterday, and he said, "Hey, I wonder if you could check the resistance of a fuse and measure a voltage drop across a fuse based on that." So I thought, wow, that's a really good idea. So I went over to our 2017 Chevrolet Bolt EV and pulled out 5 of the spare fuses that are in the underhood fuse block. So now let me put the meter back to resistance measurements. let's measure the resistance of 5 common sized fuses. So these are the little micro fuses that General Motors uses. This is a 10 amp resistor, and we are reading 7.562 milli-ohms. So roughly 7.5 milli-ohms. But we don't have to go roughly. It's 7.55 milli-ohms at 28.3 degrees Celsius. All right, now that's 7.5 ohms for a 10 amp fuse. Here's a 15. So we were at 7.5 milli-ohms on a 10 amp fuse. Now we are at 4.783 milli-ohms for a 15. Let's do the 20. 3.486 milli-ohms on a 20 amp fuse. 2.7195 milli-ohms on a 25 amp fuse, and 2.311765, it's stabilizing, milli-ohms. 2.3 milli-ohms on a 30 amp fuse. So each fuse has its own specific resistance. And I measured 2 other style of fuses, and their resistance values are very close to what these measured here. So for a certain size of fuse, it should have a certain resistance. Now, with that resistance, if we go over to the vehicle and take a voltage drop measurement in a live circuit right across the top of a fuse. So here's a 15 amp fuse right here. If we take a voltmeter, put it on millivolts, and measure right across the top of that, which I did, as you can see in this photograph here, under the hood of the Chevrolet Bolt EV over there, I measured 17.5 millivolts dropped across the left front low beam headlight fuse with the headlights on. So 17.5 millivolts, that's 0.0175 volts. Now, if we divide that by the resistance of this fuse that we just measured, which was in milli-ohms of 4.783 milli-ohms, that's 0.004783 ohms. So basically, if we take 17.5 millivolts and we divide it by 4.783 milli-ohms, the current going through that fuse with the headlights on was 3.65 amps. And it's just basic Ohm's law stuff. So you can measure the millivolt drop across a fuse if you know the fuse's resistance, which you should probably measure. There's a lot of garbage fuses for sale out there, and there's high quality fuses for sale. I'm going to buy some less than reputable brand fuses and compare them to the factory fuses that come in these vehicles and see if the resistance values are the same. They're milli-ohm resistances. I hope they are, but I know there's been some problems with some that weren't, and the fuses weren't blowing when they were supposed to blow. Okay, so with this meter, we can measure milli and micro and even nano ohms of resistance, which is useful for measuring the stator winding resistance to find a short circuit. I've shown you that we can cut an individual wire strand and it can detect the difference there. I've showed you that we can not only measure the resistance of a piece of wire, but we can tell you how long that wire is. That might be useful in somehow determining where a short circuit is. I've still got to think about that. But this is not the last video I'm going to do with this milli-ohm meter. There's got to be other uses of this meter. I'm just barely playing with it now, and I really like it. Now, the last thing I want to do is let's go over to this 2002 Prius with what appears to be a transaxle problem and measure the resistance of the stator windings in the vehicle itself. Okay, here we are under the hood of a 2002 Toyota Prius, first generation Prius. But this could just as easily be any other Prius or electric or hybrid vehicle on the road. It doesn't really matter. What matters is that we can access the 3-phase cables that go down to the transaxle from the inverter converter assembly, because that's where we are going to use our milli-ohm meter. So let's take some measurements. Okay, our first measurement will be from the U phase to the V phase, and we are reading 32.88 milli-ohms of resistance at 28.6 degrees Celsius here in the shop. Now the resistance will go up as it gets hotter, it'll go down as it gets colder. So we're looking for consistency. All right, now let's go from U to W. 35.12 milliohms of resistance. So we were at 32.89 milliohms, and now we are at 35.11. That is more than the 2 milliohm maximum allowed by Toyota. So that indicates a problem. All right, now let's measure from V to W. Now we're getting 26.98 milliohms. So our very lowest value is right here between the V and the W phase at 26.982 milliohms. Our very highest value was between U and W at 35.11 milliohms. And then we had one in the middle that has a shared branch of the Y-wound stator of 32.89 milliohms. So we have 26.9 was the lowest, 35.1 is the highest. That gives us roughly an 8.2 milliohm difference between the highest reading and the lowest reading, which tells us that there is definitely a problem with the stator windings for MG2, which is what this goes to, on this 2002 Prius, which is why it jerks really hard. It has melted through the insulation around the stator windings. It may even have contact with the stator frame, which in the next video on Mega-Ohm and Giga-Ohm meters, we will go in and learn how to check for loss of isolation or check for insulation. It's an insulation tester, so we will learn how to do that. So by comparison, I have this exact same P111 transaxle in the back room over here with a good stator winding for MG2, and all three measurements that we've done here on that transaxle measure identical. They're almost all 35 milliohms, and so that's what we're looking for. So the milli-ohm meter is a very useful but expensive but very useful tool. We can tell when stator windings are starting to melt. We don't have to wait until it totally gets to where the vehicle is chugging and kicking and spitting out trouble codes. If it's acting strangely with a little bit of jerking or pulsating as you drive, even if it hasn't triggered a trouble code yet, we can go in and take those measurements and see, because this seems to be a fairly common problem on high mileage Prius transaxles. And the newer ones with those hairpin technology stators with all those additional welds and connections have even more potential of problems. Hopefully we won't see that. This has been a review of the basic use of a milli-ohm meter. Thank you for watching.